We'd like to welcome you to the fourth module on internal curing. In the fourth module, we're going to be discussing the mechanical and transport properties of internally cured concrete. Before getting into the mechanical and transport properties in detail, we'd like to review the objectives of this module. First, we'd like to review the concept of internal curing. Second, we'll be understanding the changes that occur inside of concrete due to internal curing. Specifically, we're going to focus in on how increased hydration will improve the properties of our concrete. Third, we're going to understand the role of how the samples are conditioned, how we treat the samples before we test them, and what impact that plays on the test properties that we'll get. Fourth, we're going to understand the influence of internal curing on some of the mechanical properties, namely strength, modulus, density, and volume change. And finally, we're going to understand the influence of internal curing on some of the durability aspects associated with concrete, mainly focusing in on transport properties, freeze and thaw, corrosion, and some other items. So let's begin our discussion. And really what we want to do is we want to start off by reviewing what is good concreting practice. Here we're really talking about curing the concrete, and when we talk about internal curing, we're really talking about something that's done to the mix, a modification that's made to the mix that really enables additional curing to take place. Now ACI 308 describes curing as an action that's taken to maintain moisture and temperature in freshly placed cementitious materials. The idea behind internal curing is we're going to use some sort of a material inside of the concrete mixture to really help to maintain the moisture, to make sure that the system stays with a high moisture content. By maintaining the moisture in a cementitious material, we're going to increase the amount of reaction that's taking place, the amount of hydration that's taking place, specifically with the hydraulic reaction that occurs with Portland cement, the hydraulic reaction and the pozzolanic reaction that will occur with supplementary materials like fly ash slag and silica fume. So the whole idea is by using internal curing, we're doing what we know is a good practice for concrete. We're curing the concrete, and that's going to help to increase the reaction of the Portland cement and the supplementary cementitious materials. Now, the important concept behind this is that cement and supplementary cementitious materials require water to react. If you take water out of the equation, those materials will essentially just sit as dry powders and won't hydrate, they won't react. If we can supply water, those systems will react and will begin to fill in the porosity. So if we look at these pictures and we work our way from the left to the right-hand side, what we can see is the initial cement particles with space or water in between them. And as the cement particles begin to react, we can see hydrated products starting to fill in that pore space. The more reaction we get, the more that pore space is filled in, and the lower porosity or reduced porosity we're going to get in the system. Now, as we reduce the porosity, strength is going to go up, and the transport properties are going to go down. So as we fill in more of the space, the system is going to get stronger, and it's going to be harder for ionic species to start moving through the concrete. And this is all predicated on the cement and supplementary materials reacting. If we take water out of this equation, that reaction is going to stop. And the role of internal curing is to keep the water available for a longer period of time. Now, how do we do that? Well, we need to remember that in a cementitious matrix, we have several different size pores, and we've illustrated this in sort of a cartoon fashion in the figure on the top of the slide here. And what we can see is while we have different size pores, we need to remember that the water is going to leave the biggest pores first. So as the water starts to leave the big pores, we start to see that water leaving the system, and we start to see a reduction in how much hydration can take place. Internal curing using lightweight aggregate is based on the principle that water is going to be stored in the pores of the lightweight aggregate, and those pores are larger than the pores in the paste. So if we look at the diagram toward the bottom here, the whole concept is that water will leave the lightweight aggregate, fill in the pores in the paste. This water will then be available that can react with the cementitious material and can hydrate the system further. And this is exactly what we're after. We're after the water moving from the lightweight aggregate into the paste to sustain the hydration reaction. Now you may ask, well, how can we measure this reaction? And there are several different ways that this can be done. This can be done by measuring the non-evaporable water, and several studies have done that. But what I've shown here is just a simple example measuring the heat that's given off in a cementitious material after 3 days. At 3 days here, we can see the heat on the y-axis versus the water-to-cement ratio on the x-axis. And what we'll notice is there's a difference in the heat given off between the internally cured and the sealed concretes. Heat is a direct measure of how much reaction has occurred, so we can see that even at early ages, even as an age as early as 3 days, we're seeing a fairly substantial difference in the amount of heat given off, the amount of hydration reaction, and this tells us that the internal curing is doing what its intention is. It's hydrating more of the cement. Now the other thing to think about here is this is done at a relatively early age. This is done at about 3 days. If we continue this type of a measurement, we were to do this and look at this at a later period of time, we would see the difference between the red and the blue dots starting to become larger, meaning that the internal curing is going to be hydrating more and more of the system, and we would see this gap start increasing at higher and higher water to cement ratios to show that we would see an increase in the degree of hydration. Some additional studies will show that after about 90 days, we'll see 5 to 10% more hydration typically in an internally cured system than we do in a sealed system. Now, why is that additional hydration occurring? Well, we can look at this graph that's been adapted after Powers and Brownyard's work, and the whole idea here is that as we decrease the humidity inside of the system, as we decrease the available water inside of the system, there's less water available to take place in the hydration reaction. So as the system dries out, as it reacts, as water leaves the large pores, it becomes harder for that water to react in that system. We hydrate less and less of the system. By providing additional internal curing water, we can keep the relative humidity high. We can keep the water activity at a point where it can hydrate with the cement, and we react more of the material. So at this point, really what we're saying is nothing that we haven't already learned in sort of good concreting practices. By keeping water inside of our concrete, we're going to react more of the cement, and by reacting more of the cement, we're going to improve the overall performance of our concrete. So some thoughts that we really want to keep in mind here as we start to move forward. You may ask the question of, well, what happens when we start to put these lightweight aggregate particles in? Will they have an impact on the strength, or because it's a porous particle, what's going to happen? Well, typically we have a trade-off that's going on. So the lightweight aggregate may reduce the strength slightly, but again, remember we have the internal curing that's reacting more of the cement and more of the supplementary cementitious materials. So generally we see that the strength is usually within about 5 to 10% in either direction of the conventional concrete. Sometimes we may see it being slightly lower, and this would essentially be the lightweight aggregate particles reducing the strength a little bit. Sometimes, however, in the internally cured system, we see the strength being slightly higher, and this is because we're increasing the reaction in the matrix, we're increasing the strength of the matrix, and we're decreasing the transport properties. But really the overall takeaway is generally we don't see a huge difference in the compressive strength between a plain system, which is shown here as the solid lines, and the dashed system, which is the internally cured concrete, the blue lines being a low water to cement ratio of 0.3, and the red lines being a water to cement ratio of 0.5. The general takeaway is you can expect to have very similar compressive strength between a plain and an internally cured concrete. But we also need to remember that how we handle the sample before we test it can be very important to the properties that we're going to measure. So what we want to do is we want to talk about how the samples are handled, because many times we may think of, well, we just put our samples into a water tank and then we want to try to evaluate those properties. And what I would actually ask is, does that really represent what we're getting from a concrete that may be in the field? And when we do this, we need to remember that for many tests we're going to use water curing, But internal curing really provides water to a system that's not otherwise available. So for example, in a field case where you may not be doing water curing, your concrete may more closely represent something that's a sealed system at best, where we've put a curing compound on, or we've essentially prevented evaporation, or even a concrete that's begun to dry slightly. And the internal curing will provide water for that. So it's really important that we consider exactly how we store our samples, exactly how we condition them when we start to do evaluations that start to look into how good is the internal curing, or how much does the internal curing change the overall properties of the concrete. So to get into this a little bit more, in some of the earlier modules we've talked about the role of Power's model. We've talked about the role of what happens when the cement begins to hydrate. And what we can see here is Power's model again illustrated, where the x-axis is the degree of hydration, the y-axis is the volume proportions inside of the paste. And as the cement reacts with water, we can see that the dark blue and the gray volumes will decrease, and that will be replaced by the gel solids, which is our calcium silicate hydrate, our calcium hydroxide, which is essentially going to be that yellowish region, the gel water, which is our aqua region, and we also will get some chemical shrinkage going on, which is going to be open space inside of the system. Now, as we start to think about this, we have our cement reacting with our water. We're going to have pores that start to partially empty, and this is going to be partially emptying because of that chemical shrinkage, and it's going to cause sort of that vapor-filled space to form inside of the matrix. So if we did nothing else and we just looked at a sealed system, what we would see is as the water and the cement react, we would start to now have pores inside of our concrete. Those pores would be partially filled with the fluid, the water, previously shown as the gel water or the capillary water, and they would also be partially filled with a vapor-filled space, which is actually the chemical shrinkage. And what we're trying to show here on the right-hand side is the typical pore, which may go from a very large pore at the top to a small pore at the bottom, with the yellow region representing the vapor-filled space and the blue region representing the water that's still available inside of the system. Now, if that system were to dry out more, let's say by external drying, what we can see is additional water will be lost, and that will lead to essentially a higher pressure inside of the fluid and a sharper meniscus inside of the fluid. However, if we were to provide additional water, what we would see is that we would essentially reduce that meniscus. We would start to get the pores much more filled, and we would reduce the stresses that are inside of the fluid inside of the system. So really, when we start to look at these different cases of how the samples are cured, we need to remember that we're changing the pressure inside of the fluid, we're changing the internal relative humidity of our concrete, and we're changing the moisture content that's inside of our system. So the top would be a case where we're adding additional water to the system through water curing or something like that. The middle case would represent where we've essentially sealed the concrete, or we're using a curing compound where we essentially remain moisture neutral, but vapor-filled space opens because of chemical shrinkage. And on the bottom, we have chemical shrinkage being coupled with some sort of an external drying, which is opening up additional empty space inside of the system. So it's important to have this picture and sort of how this represents different cases that you may come in contact with real field applications. So the whole idea is, by providing internal curing, we're providing additional moisture, leaving the lightweight aggregates filling in the pores, which would be very similar to water curing a concrete system. So again, it's important that we remember that when we look at porosity, the pores are going to come in two different sizes. We're going to have the gel pores, which are the small pores. They're going to be part of the hydrated products, and the capillary pores, which is really what we're going to be controlling with our water to cement ratio. But there's a direct relationship between the size of the pore that empties and the relative humidity that's going to develop in the system. Said another way, the smaller the pores, the more tension we're going to place into the fluid, the more we're going to constrict that fluid movement, the less it's going to be available to participate in the hydration reaction. So now if we look at different concretes that are cured in different ways and we measure the relative humidity inside of these systems, effectively what we're doing is we're measuring the size of the pores that have been emptied under these different conditions. So if we go from left to right, we can see the first 4 bars represent a wet curing condition. This is going to be our concrete placed underwater. The next 4 bars are a moist curing condition where this is placed into a fog room. The next 4 bars are going to represent a sealed condition where we are not adding water, we're not losing water from the system. And the last 4 bars represent where the samples have been placed into a drying condition after the first 24 hours, into a 50% relative humidity room. Now what we're going to do is we're going to measure the relative humidity inside of these different systems. And what we can see is as we go, as we would expect, as we move from wet curing, moist underwater curing, all the way over to drying, the general trend for each one of these mixtures is we'll see the relative humidity decreasing. The big takeaway from this, though, is it's a much bigger decrease in the relative humidity for lower water to cement ratio mixtures. So the blue mixture and the solid represents the plain 0.3 water to cement ratio. The blue represents a 0.3 water to cement ratio concrete. The red represents a 0.5 water to cement ratio concrete, while the hatched lines start to talk about those same systems that have been internally cured. What we can see is that as we move for the 0.5 system, we see a slight reduction in the relative humidity when we go to a sealed case, mainly because only a slight amount of water is going to be absorbed, because in a 0.5 case, we're only emptying the really big pores, and we're not essentially generating a lot of underpressure inside of that fluid. As we move to a lower water to cement ratio system, though, we're going to see that the relative humidity can drop off substantially. And if we remember this inset at the top, which was the powers graph that showed us how the amount of reaction changes with the relative humidity, what we can start to see here is at 80% relative humidity, the reaction is much lower than if the system had been fully saturated or fully wet with a very high relative humidity. So again, in the sealed case or in the drying cases, we can see a huge benefit of internal curing. Those benefits aren't seen as much when you get to the wet case, because the wet case is supplying additional moisture from the outside. That moisture is going in and filling in the pores, doing exactly the same thing that we would expect the internal curing to do. However, in the sealed case and the drying case, we can see that we're getting about 8%, 10% increase in the relative humidity just from the internal curing in the 0.3 water to cement ratio case. So the big takeaway is the curing condition can play a large role in how our different cementitious materials are compared. And when we think about internal curing, we're typically thinking about trying to represent where we're not going to supply additional water in the field due to water ponding. So maybe a sealed condition or even a drying condition may be the best way to represent what we would expect to be happening in the field. Now, how does this impact the overall other properties that are going to start developing in the system? How does the way the system is being conditioned, how does that make a big difference? Well, if we look at this particular slide, on the bottom what we can see is a comparison of the plain and internally cured concretes that are water cured and the plain and internally cured concretes that are effectively dried in these systems. Again, the solid line represents the plain system, the dashed line represents internal curing, and what you can notice is when the systems are water cured, we get a very similar response for both the 0.3 case, which is shown in blue, and the 0.5 water to cement ratio, which is shown in red. That's not surprising. Whether it's water cured or not, whether it's internally cured or not, when you're water curing, there's a sufficient amount of water inside of the system being supplied to the system that's going to hydrate more and more of that cement. So both of these systems are sitting in water, which allows the concrete to draw additional water from the surroundings, filling in the pores. However, the bigger takeaway here is when we look at the graph on the right-hand side, and there are two things that we really want to take notice of. One is the difference between the dashed line and the solid line, and that really demonstrates the benefit of internal curing. So here all of a sudden you can start to see some benefits of the internal curing inside of the system. The other thing to take away here is really this green line that's been added. That green line is the effect of water curing. So what you can start to see here is the internally cured concrete gives us similar or slightly better performance than our water cured concretes, especially at earlier ages, right? But it gives us substantially improved performance when we start to look at the plain concretes. And this really shows that internal curing is doing the exact same thing that we really want for our concretes. It's providing that additional water that's allowing hydration to take place. It's really doing what we want to get good curing on our concrete. So what are some of the takeaways from the sample conditioning portion of what we're discussing here? Frequently, water curing is the norm. We take our cylinders, we place them into a water bath, and we use that as a standard way that we'll measure the properties of our concrete. However, I think we really need to think about how our samples are stored when we're trying to determine if internal curing is effective or not. Internal curing is really going to do the same thing that water curing is doing. It's going to keep the relative humidity high, which is going to hydrate more of our cement or cementitious materials. Water curing and even moist curing in a high fog room or 100% relative humidity room is going to add water to our concrete to fill in some of those pores. This is going to add water to the plain concrete, and it's going to add water to the internally cured concrete. And in both of these cases, what we're going to typically see is that the plain and internally concrete are going to behave in a fairly similar manner. However, when we look at concretes that may be sealed or concretes that may be drying, the supposition here is this may actually be closer to what we see in many of the field cases, and here we're going to see a big distinction between the internally cured and the plain concrete because we have that additional water that's helping to hydrate more of the cement, helping to hydrate more of the supplementary cementitious materials. And what we're going to see is that the internal curing is going to get us very close to the case where the samples were water cured. Now what I'd like to do is I'd like to take a little bit of a segue here and jump into to move away a little bit from the sample conditioning and really to start to talk about the mechanical properties, because very frequently we get a question of, well, if I start adding these lightweight sand particles, what's this going to do to the concrete design? What's this going to do to the overall properties of our concrete? And at this point, I think it's really important that we know that lightweight concrete has been used widely for nearly a century. Here we can see some examples. These are examples where high performance or high strength concretes have been made using the lightweight aggregates inside of the system. But I also want to consider some of the other details that are going on when we start to talk about internal curing, because we want to remember that really the way that internal curing works is it replaces a small portion of the sand that's inside of the system. So generally our coarse aggregates are going to be very similar, our paste is going to be similar, and we're going to replace somewhere between maybe 20 and 40 or 50% of the sands typically in a concrete mixture. And we're going to have three different phases that we worry about. We're going to have the paste phase. This is the cement and water that's reacted. This is the phase we typically think about as the glue. We have the aggregate phase, which is shown in black here. This is pretty straightforward. These are the rocks, this is the sand, this is the aggregate that's been added to the system. And the final phase that really gives us our third phase in the system is the interfacial transition zone, which is shown here in orange. And this is the region where the paste comes in contact with the aggregate, and we frequently hear this as being described as a porous region inside of concrete, presumably because of particle packing issues that happen around the aggregate where the cement can't pack as tight as it would in a normal paste. In addition, calcium hydroxide will preferentially precipitate on the aggregate surfaces, and that calcium hydroxide can leave porosity behind when it goes away. So these are the three phases that we're going to be talking about as we move through the system. The paste phase, the glue phase that's kind of in the middle, shown as gray, the aggregate shown in black, and the interfacial transition zone shown in orange. Now, in conventional mixtures, what we will notice is that the interfacial transition zone around lightweight aggregate tends to be better than it is around a normal weight aggregate. When I say better here, what I'm saying is it's more dense and more uniform. And if we look at this picture to the right-hand side, what we're going to notice here is the lightweight aggregate on the bottom here, shown as this porous material in the center, where these pores have been expanded inside of the lightweight aggregate. What you'll notice is there's a very, very small interface at the aggregate edge, and this is mainly because the alumina and silicate at the surface of the lightweight aggregate will react with the calcium hydroxide and really not have as much calcium hydroxide precipitating on the surface of the aggregate. This means that the modulus between the aggregate and the matrix is going to be much more similar. There's going to be less cracking in those systems. There's going to be less of a porous region in those systems. We're going to see less bleed water developing around the aggregate because water can actually be absorbed here. And what we're going to see is that this region, or interfacial region, is not really as well defined as it is around a normal sand particle, because now we're not going to have that sharp boundary. We're not going to be collecting water, and calcium hydroxide can react with and actually go inside of the lightweight aggregate. So part of this discussion is that when we use lightweight aggregate, we typically see a much smaller influence of an interfacial transition zone. So lightweight aggregate concretes can be designed to have very similar strengths to normal weight aggregate concretes. Internal curing is not any different at all from this, and in fact we typically see very similar strengths because we're only replacing a small portion of the sand inside of the system. So as I mentioned before, generally what we see is the compressive strength of internally cured concretes being very similar to conventional concretes, generally within a 10% reduction to a 10% benefit. You may say, well, why would we see this benefit? Again, if we're adding in a porous, lightweight aggregate, this should be maybe less strong than the conventional sand that we're using. Remember, we're getting additional curing that's taking place, so we're hydrating more of the cement. We're also having a lower impact of the interfacial transition zone. So frequently what we see is a very similar compressive strength when we're starting to replace some of the conventional sand with lightweight aggregate sand. Now that talks about compressive properties, but frequently people want to look at other properties in the system, and direct tension is often very difficult to do. So people will frequently measure things like splitting tensile strength. This geometry can be shown at the bottom, where we're going to take a cylinder, we'll turn it on its side, and we'll measure the stress in the one direction, and that will be very similar to a tensile strength at failure. Now, if we do these for the internally cured concretes, the results become a little bit more difficult to interpret, but if we take a second to look at these, they really seem to be logical. First, we can look at the 0.3 water to cement ratio concrete. This is shown in blue, and what we will typically see with our high strength concretes, this happens to be a compressive strength of 70 MPa, 0.3 water to cement ratio. We see a slight reduction in the compressive, or the tensile strength of these concretes. Here we can see the internally cured concrete has about 15% lower strength at 7 days, and maybe a 6% lower strength at 28 days. This is for a high strength type of matrix, where this porous aggregate now is really acting as a potentially weak plane for the fracture to take place inside of those systems. However, at lower water to cement ratio, lower strength materials, higher water to cement ratio, as we see here with the red curves, we can see a very similar strength at early ages, and by later ages we're going to see a slight increase, and this is because the degree of hydration is much more important than the slight reduction in strength we're going to see from those porous particles. So it's very important when we start to think about these items that we realize that there's not going to be one universal rule. It's going to depend a lot on the matrix that we use for these materials. So typically in a lower strength concrete, we're going to see a slight improvement in the tensile splitting strength. If we get to very high strength concretes, we're going to see that the benefits of hydration are going to be moderated by the porous particle itself, and we can see a slight reduction in the splitting tensile strength. Similar issues have been observed by some work at Auburn, where Bird and Schindler have looked at a concrete that has a compressive strength of about 35 MPa. This is a typical bridge deck concrete. What I'm going to mention here is they designed these internally cured concretes to have a specific density of about 135 pounds per cubic foot. And what they saw in all of these cases were higher split tensile strengths for the internally cured concrete than the conventional concrete. And the whole idea here is really related to the internal curing water. It's going to be benefiting the hydration of the system, increasing the overall strength. So here what we can see on the top is the compressive strength for the control mixture shown in black. And what we can see is depending upon how much of the lightweight is being used, you can see a slight increase or a slight decrease in the overall compressive strength. However, on the bottom, we're going to see the splitting tensile results. And what we'll notice here is that for the control shown in black, after about the first day or two, it has the lowest strengths of all the other mixtures. This is because of the additional hydration that's taking place to help increase the split tensile strength. Now, to move on past just the tensile strength, we can also look at the elastic modulus. And as we mentioned a little bit earlier, it's important to remember here that the lightweight aggregate tends to have a slightly lower modulus than most of the normal weight aggregates that are being used. So it tends to be more like what we see in the matrix. We can estimate the elastic modulus using the standard ACI formulation, where we can say that the modulus is equal to 33 times the density of the concrete raised to the 1.5 power times the square root of the compressive strength, and that's shown here. Now, we can also look at this in a slightly different way, that if we had a paste with the same degree of hydration, what we would notice is that as we altered the aggregate volume fraction, we would be seeing the elastic modulus of the composite changing. What we'll notice here is that the main effect that we're seeing here is really due to the aggregate. So if we have a lower elastic modulus of the lightweight aggregate, we're going to see the point on the far right-hand side of that graph decreasing because the stiffness of the aggregate is decreasing. And what we'll see here is that since the modulus of the aggregate is actually becoming slightly lower, what we're going to notice is the overall modulus inside of our internally cured concrete would be expected to be slightly lower as well. Now, the interesting part about this is this assumes that the paste is the same in these systems, and what we typically see, again, is more hydration in the paste. So we'll see the modulus of the paste shifting up slightly. We'll see the modulus of the aggregate shifting down slightly. The aggregate being the right-hand side of the curve, the paste being the left-hand side of the curve. So what we'll typically notice is that these two effects will sort of work to make a much smoother transition here between the paste and the modulus of the lightweight aggregate. So if we start to look at this system, what we're going to see is that the internally cured concretes will have a slightly lower modulus than the same concrete made with the normal weight aggregate. The deformations in the aggregate are going to be much more similar to what we see in the paste. So typically we see less microcracking taking place. And in addition to this, when we start to talk about concretes that are restrained, like a bridge deck, like a floor, where they're under a tension, the lower modulus can actually be quite helpful in that system because it's going to reduce stresses out of that system. Now, you can estimate this using a law of mixtures. I will not get into this in great detail, but if you know the properties of your lightweight aggregate, you know the properties of your normal weight aggregate, you could go through and use a law of mixtures approach to determine the overall modulus of the concrete. Again, just to show some examples of this, the basic idea here, solid being our plain concrete, the dashed lines being our internally cured concrete. As we use the lightweight aggregate sand particles, we'll see a slight reduction in the elastic modulus. The reduction will become bigger as you move to higher strength concretes. So here in the red system, we'll see a slight reduction in the modulus. As we move to the 0.3 water to cement ratio, we'll see a bigger difference between the plain and internally cured concretes. Now, the final thing I really want to mention on that is having a lower modulus can actually be beneficial when the concrete is restrained and when we're worrying about cracking, because lower stresses are going to be building up inside of the system. Now what I'd like to do is I'd like to transition from the mechanical properties on over to start to talk about the durability properties of the internally cured concrete, or the durability of concrete that contains lightweight aggregates. And here we can see some examples of concretes that have been made with lightweight aggregate concrete. Here is a concrete ship that was made with lightweight aggregate concrete that was tested at 28 days and had a compressive strength of about 4,000 psi. Tested many years later, 60 years later, the strength was in excess of 8,000 psi, and the porosity had really filled in inside of these systems. Now, the main principles of internal curing that we're going to go over are the same principles that we've been talking about, and the same principles that we're after when we start to look at why we cure concrete in the first place. On the top, we see two figures where we show the effects of, by adding additional water, we can react more of the cement. By reacting more of the cement, we fill in more of the porosity, we reduce the porosity in those systems, and we densify the system. By doing this, we've made our internally cured concrete stronger. We've also increased the difficulty that an ion is going to have to move through that system. The second benefit we just talked about when we were talking about the mechanical properties, that the lightweight aggregate typically has a smaller interfacial transition zone. And if we think about this, instead of having an interfacial transition zone around all the particles like we see here as this red region around all of the yellowish orange aggregates inside of the paste, if we can replace 30 or 40% of the sand particles that don't have this interfacial region, what we can start to do is we can start to depercolate the interfacial transition zones in internally cured concrete. So what does this mean? Well, if we look at the figure at the bottom of the slide in the center, if we had a chloride ion that was trying to move through from the top to the bottom, and these red regions are more porous and easier to flow through, you could expect that a chloride ion would move right through the interfacial transition zone, right through the red region, from the top to the bottom of the concrete. However, if we can go to a lower water to cement ratio concrete and a condition where we start to depercolate those interfacial transition zones, reduce or remove those interfacial transition zones with the presence of this lightweight aggregate, what we can see is now an ion may start to move through that red interfacial transition zone, but all of a sudden there's not a completely connected path from one side to the other. By depercolating this system, we've now made it much harder for ions to be transported through the system. Now, just to show, to go from sort of the cartoon version of this onto some actual images, what we can start to see here is that by using the internally cured lightweight aggregate concretes, we're going to densify the system. So here we can see some plain concretes at the top. We can see some internally cured concretes on the bottom. And the two things to really take notice of is as you move from the plain concrete on the top to the internally cured concretes on the bottom, you will notice a substantial reduction in the porosity of those systems. You'll also notice less interfacial transition zone around the aggregates. This is exactly what we've been talking about in these cases. Okay, so one of the questions that we frequently get from people is, well, that sounds great, but the lightweight aggregates have their own pores, and these pores are bigger than the pores in the paste, so won't this increase the transporter permeability? So there are several studies that have actually looked at this. Zhang and Gorov have looked at this, and they've essentially said that the permeability of the high-strength lightweight concrete is much more dependent on the porosity and the permeability of the paste than it is of the lightweight aggregate. The whole idea behind this is that the lightweight aggregates themselves will actually empty out of water, and it's very difficult to resaturate them even if the sample is placed back in water. It takes a long time for this to happen. Henk and Sifkin showed that it's very, very difficult to resaturate a low water to cement ratio internally cured concrete unless you go and you actually use vacuum in the overall system. Now, as we start to talk about the transport of different species or the transport of fluids through the concrete, it's important that we look at the words that we're going to use to describe the different mechanisms. So here we've really talked about 3 or 4 of the main mechanisms that happen inside of the concrete to allow fluids or allow ionic species to move from one side to the other. The top here we'll see an ionic diffusion, and this is really set up by a concentration difference inside of our samples. That one side of our sample we may have a high ionic concentration. Inside of the pore fluid of our concrete we may have a lower concentration. This could be an example of a water saturated concrete that's in contact, for example, with a salt water or with the icing solution on top of the surface of our concrete. Over time, those chloride ions or other ionic species will want to move through the concrete. They move by a mechanism called diffusion. Capillary sorption is the next mechanism, and this is really the filling in of the pores inside of a porous media or inside of our concrete by water absorption. This is a very fast mechanism and can really be looked at here as water being sucked up into the concrete. Permeation is the next one, where we're really driving water in by a pressure gradient, and wicking is where we're essentially having a combination of a diffusion and absorption and then essentially a drying out on the other side of our concrete. And what's happening is that by the drying effect, we're evaporating water off of our concrete, but we're leaving salts or we're leaving ionic species behind, and they can actually create a higher concentration right behind that drying front inside of the system. So as we start to talk about all the different ways that we're measuring the effects of internal curing on our transport properties, it's important we keep in mind the idea of diffusion or the idea of absorption, which is the water filling in the pores, permeation, where we're going to have some sort of a pressure that's driving the fluid throughout of our concrete. So what we can look at here is we can see some plots of how the water gets absorbed into concrete for different water to cement ratios, shown here as low water to cement ratio being the red case of a 0.3 all the way up to a 0.45. Shown here is the black dots, and then the x-axis on these axes will essentially say how much lightweight aggregate is being used to internally cure the concrete. So at 0%, we essentially have a plain concrete, and at 100%, we're essentially at a point where we're using the Bent's equation, which we can see here, which is supplying 100% of the water that would replace the volume created by chemical shrinkage. Now the two plots report the results of absorption in a slightly different way. So it's important to notice that the samples had been conditioned by leaving them at 65% relative humidity for a long period of time. Long period of time here being over a year. And what we can see here is that as we internally cure our concrete, both the initial rate of water absorption in the plot on the left-hand side, talking about initial sorptivity, that's the rate of water absorption. And the plot on the right-hand side, which is the total amount of water that's being absorbed, we can see that both of those decreases we use lightweight aggregate in the system. This can be directly attributed to the fact that we've hydrated more of the system, so we've reduced the porosity, and we've cut down on the interfacial transition zones inside of those systems. And what we can see is that for a 0.3, a 0.36, a 0.42, and a 0.45 system, the internally cured concrete has a slower rate of absorption and less overall absorption than we see in the typical system. Now, we can think of this a little bit if we look at these graphs here, where we can say that we're getting an additional effect of the hydration, which is filling in the porosity. We're getting the additional effect of essentially having a more dense interfacial transition zone. But if we look at the graph on the left-hand side on the bottom, what we can say is, well, this is the water that's absorbed after 8 days, and we're plotting the effects of the water to cement ratio in the plain system on the black line, and we can see two internally cured cases. Half of the internal curing water shown as the red dot, and the internal curing water following the Bent's equation shown here as the blue dot. And what we can see is that while they were prepared with a water to cement ratio of 0.3, they're really acting like a concrete that has a lower water to cement ratio. And in this case, it happens to be a water to cement ratio of about 0.23 for the case that was internally cured to replace all the water that was that was lost in the chemical shrinkage, essentially the chemical shrinkage reaction. Now this is important because this is effectively saying that even though we're casting a 0.3 concrete, it's really behaving more like a 0.23. And if you just look at water to cement ratio, that may be a little bit confusing, but if we move over to the right-hand side and we say, well, this is the absorbed water versus the total porosity minus the gel pores that we have in the system, so really the big pores that we're going to have in the system, what we can see is that this all starts to make sense. We've increased the degree of hydration, we've reduced the interfacial transition zone porosity, and what we really see now is everything falling along a single line. So we can essentially look at this, and we can look at this in terms of effectively having a single equation that would describe the overall response. And here we can see the absorption equation that says absorption is equal to a few constants times the amount of internal curing that you're using in the system. Again, the more internal curing you see, you can see a % reduction of the amount of water that's absorbed. So what we'll notice here is we'll see a reduction in the initial absorption, in the secondary rate of absorption, and the total absorption, but in general the case is about a 50% reduction with internal curing. Now, in addition to what we were talking about before, we can notice that salt water gets absorbed or diffuses through the pores inside of the concrete. And one way to account for this diffusion process is to use Fick's second law, or the error function approximation of Fick's second law, which is shown on the top of the slide here. But the basic idea that we're trying to do with this is we're trying to calculate how long it takes the salt, the chloride ions from the salt, to move through the cover of concrete and to reach the reinforcing bar, where at a sufficient concentration, those chloride ions will help to depassivate the steel and lead to corrosion. So the whole idea here is we want to use Fick's second law or some other sort of approach like the Nernst-Planck approach to estimate how long it will take the chloride ions to move from the surface of the concrete to reach a sufficient level at the bar, a critical level at the bar, and this is going to depend on, 1, the depth of the reinforcement, and 2, the quality of the concrete. So in a lower quality concrete, maybe shown by the purple line, we'll see that we'll reach that critical level much faster than in a moderate, the yellow line, or good quality concrete that we see here shown in green. Now, internal curing will reduce the depth of penetration of the chloride ions, and here you can see some results from Dale Bentz at NIST, where you can essentially see that looking at the plain control concrete in blue and the internally cured concrete shown here in the salmon color, what we'll notice is that the chloride ions get much, they're reduced, the depth of penetration is reduced at 28, 56, and 180 days. By reducing the penetration of the chloride ions, it's going to take longer to reach the reinforcing steel, and the real reason that this is being reduced, we're hydrating more of the cement. That's the first thing. The second thing that we can see here is, in addition to hydrating more of the cement, we're really reducing the interfacial transition zone regions. Here we can see the same type of information where we're looking at the depth of penetration as a function of time, and what we'll see is in the internally cured concretes, we typically see less penetration at sufficient depth inside of the system, again due to the dense microstructure and the less connected interfacial transition zone. Now, another way that this can be measured is by using the electrical resistivity or the electrical conductivity of the concrete. So here we can see an internally cured concrete. Again, this is very similar to what we saw slightly earlier. Different water to cement ratios plotted against the overall conductivity of a mortar shown in black. When we use the internally cured concrete, either the blue diamond or the red dot representing the amount of internal curing water that replaces an equivalent volume of what's lost due to chemical shrinkage. Here we can see that while we've casted a 0.3 water to cement ratio, the conductivity is really more like a 0.23 water to cement ratio because of increased hydration and reduced effects of the interfacial transition zone. Now, why is conductivity important? Well, conductivity can be directly related to the diffusion coefficients of our concrete. So what we're really saying is that internal curing is going to help reduce the diffusivity of ions inside of our system. And here we can see an expression where we look at that conductivity and we can see it for these different water to cement ratios. And again, we see about a 40 to 60% reduction in the overall conductivity of those systems when we start to internally cure our concretes. This means that it's going to be harder for the ions to move through the system, which means we would expect to have an increased service life. Now, one thing that should be remembered here is that typically when we talk about conductivity, we consider that the aggregate is non-conductive. So the aggregate itself is non-electrically conductive. However, in lightweight aggregate concretes, when the lightweight aggregate fills with a pore solution or fills with an ionic solution, the aggregate can actually become conductive. This will increase the conductivity of the overall system. So what we've shown here is in a simple plot is we've essentially looked at the role that conductive aggregates could play in this system. In everything that I'm going to show here, we don't consider the role of conductivity of the aggregates. However, if you're looking at a case where you're using more than just the internally cured sand, you're replacing much more than you need to, or you're looking at the coarse aggregates, you may see a higher conductivity. This is because of the fact that the aggregates themselves are going to conduct in the system and you're not just measuring the paste properties. And if this is a question that arises, we'd be happy to help you to do the calculations to figure out how to account for the conductive aggregates. But in general, this isn't something that we need to worry about with internally cured concretes where we're just replacing a small portion of the sand, and that portion of the sand is to replace the internal curing water. So we're going to steer away from the correction for conductive aggregates, and everything else that I'm going to present is assuming that the aggregates are non-conductive, which is conservative for the remainder of the slides here. In addition to looking at conductivity, Holm has looked at freeze-thaw behavior, and one of the things that we can notice here is that if we get some air drying into conventional lightweight aggregate concretes, we'll typically see that they'll behave much better, and the whole reason for this is the drying will pull the water out of the lightweight aggregate, out of those big pores, and get it into the paste, and then it becomes very difficult to resaturate those pores over time. So the prior studies have shown that drying is beneficial. Again, recall that the reason that this is happening is because the water is being pulled out of the aggregates. In internally cured concretes at low water to cement ratios, 0.42 and lower, self-desiccation and chemical shrinkage are going to pull the water out of the lightweight aggregates themselves. So if we expose our concrete to freeze-thaw after, let's say, 18 or 24 hours, this is not going to be a typical concern any more than we would have in a normal conventional concrete, because what's happening here is the water is being pulled out of the lightweight aggregate the same way we would have seen this with drying in a much more conventional concrete. So again, to push in a little bit more on the freeze-thaw behavior here, the performance of lightweight bridge deck concretes is at least as good as normal density concretes, and this is from a study from Brown. Experiments have shown that plain and internally cured concrete behave very similarly when they're exposed to freeze-thaw if they're properly air entrained. So the whole idea here is that if you've properly air entrained your concrete, whether it's a plain concrete or an internally cured concrete, that concrete is going to be freeze-thaw resistant. And the reason for this is because at a sufficiently low water to cement ratio, chemical shrinkage is going to occur that's going to lead to self-desiccation, which will actually pull the water out of the lightweight aggregates to hydrate more and more of the paste. As it pulls the water out of those lightweight aggregates, they're going to be left as vapor-filled spaces, and it's going to be very, very difficult to fill those vapor-filled spaces back in. So just to confirm that, what we've shown here is a series of studies that were performed where we used a mixture that was very similar to what would be used in the state of Colorado for 5 different mixtures here, and what you can see is the ASTM C666 failure limit showed as the red line, and then we can see a plain Class H mixture from Colorado compared to 4 different internally cured mixtures, and each one of these has a very, very similar behavior over 300 freeze-thaw cycles. The whole idea behind this is because the aggregates themselves are durable, water is pulled out of the aggregates for internal curing, and what we're going to notice is that with a properly air and cured concrete, we're going to see that this is going to behave very well in freeze-thaw. In addition, people have examined alkali-silica reaction with internally cured concrete. So the whole idea here is that the alkalis will come from the cement in the environment. They'll react with the silica, the amorphous silica that can be in certain aggregates. That reaction will form a gel. That gel will take on water, which will swell, and if it's sufficient, can cause cracking. The question was, can internally cured concrete help with this? Shin reported results for several different systems here, looking at reactive systems, looking at reactive sands in a 15 and 28% condition, and non-reactive sands in a 15 and 28% replacement level. And really the whole idea here was to look at some of the pros and cons. So the pro is that internal curing will decrease the porosity, which will make it harder for fluid to get into our concrete, and water is very important for the ASR reaction. The lightweight aggregate itself will provide space for the gel to form where pressures may not be developing and may allow more gel to form in the system. But probably the most important pro is that you're essentially using a dilution effect. So here, especially if your sand is the reactive aggregate, you're taking out a fairly substantial portion of what's reacting and replacing it with a expanded lightweight aggregate that is typically non-reactive. So you're diluting the potential for the ASR to develop. One of the cons in this case, or one of the negatives, would be the lightweight aggregate itself is providing more moisture. That moisture would essentially be present for the ASR reaction to occur. So if we look at some examples here, what we can see is 5 systems that were measured and reported on by Shin. And what we're looking at here is a reactive system. So this is a typical mortar that has just reactive sand in it. Those reactive particles are going to be expansive. And what we can see is that after a relatively short period of time, we're going to see that reaction taking place, and we're going to see expansion occurring in the mortar bars. In red, what we've shown here is what happens if you just dilute the sand by replacing 15 or 28% of the sand with a non-reactive aggregate. So this is not an internally cured case. This is just replacing reactive sand with a non-reactive sand. What you can actually see is a delay in the time of expansion and a delay in the overall expansion that's occurring. The blue, however, with the open symbols representing a 15% replacement and the closed symbols representing a 28% replacement, what we can see here is that the internal curing is actually even more effective than just diluting the system, just replacing the sand with a non-reactive particle. Here what we're actually seeing is we're seeing that apparently the benefits of the internal curing actually override the effects of just dilution, and we're seeing an even greater delay in the overall ASR reaction that's taking place in these systems. So here what we'll notice is that we're delaying the reaction with the addition of the internal curing, presumably because we're densifying the system, but we're also using the lightweight aggregate to provide space for the expansive gel pressure that's being formed to essentially be reduced in these systems. When we look at the 28% replacement here, we can see even a more substantial reduction in the overall expansion that's occurring in the system. Now, all of this is not to say that this is the only way that to reduce an ASR reaction, but it's just describing the role that internal curing could have on this overall response in these systems. And again, this is looking at a system where it's the sand that's reactive, so you're getting a benefit of dilution. You're also getting the benefit of having additional space for the ASR gel to form. Similar results have been seen by Bentz, where he was looking at internal curing to slow the expansion due to sulfate attack. Here you can see that the the internal curing did work to increase the time to expansion, mainly because of accommodating the expansive the pressures and products that are forming in the lightweight aggregate pores, but also here you can see some examples where the lightweight aggregate was used to deliver material that would have a higher viscosity, and that would essentially help to delay the transport properties as well. But again, the internal curing here is working simply by providing additional space in the pores of the lightweight aggregate to reduce the effects of sulfate expansion. Corrosion testing, this has also been widely undergone, but one of the things that I want to point out here is that generally if we run just straight corrosion tests, we see a slight benefit of the internally cured concrete because of the denser concrete, because it's harder to transport through the system. But what I really want to talk about is what happens when you have the corrosion potential taking place in a planed concrete that can crack and corrode, and an internally cured concrete exposed to the same types of conditions. So here what we know is that the internally cured concrete is effective in reducing shrinkage, and we saw that in the third module. But in addition to reducing shrinkage, it's really reducing the shrinkage cracking. We also have seen that internal curing can help to reduce the transport properties, and this is going to make it harder for the chloride ions to move through our concrete. So here what we can do is we can see a large slab. This is a 15-foot long slab that was instrumented with a rebar that was monitoring the corrosion behavior, and the idea was to really try to couple together the big benefits of internal curing that we see. The first is we're going to reduce the shrinkage and reduce the potential for cracks that form. The second is we're going to get an additional benefit and reduction in transport properties, but it's really the combination of these that have the potential to improve the overall service life of our concrete. So here you can see some of the details. I won't spend a lot of time on the details of this particular experiment, but we've got a section that's about 15 feet long, and in the center we have an instrumented rebar. And that rebar is being instrumented in the center. We're going to look at a 0.3 plain concrete, a 0.3 internally cured concrete, and we're going to make sure that the crack is going to occur in the center by using some small notches to make sure that that's going to be a weak plane in the system. In addition to monitoring corrosion, we're using strain gauges on the steel restraining beam to monitor stress development and cracking inside of the system. Now, the rebar that's inside of the center of the concrete is actually hollowed out, and we're going to place small sensors that are even right with the surface of that steel, so that when this is placed into the concrete, what we're going to be able to measure is how fast these sensors go into corrosion, so we can get an idea of how far away from the crack we may be getting corrosion inside of these systems. Now, before we get into the corrosion portion of this, we really want to look at the cracking portion of this. And what we can see here is the plain mixture shown in blue with the internally cured mixture shown in green. Now, the internally cured mixture, we get a little bit of compression in the concrete, and we don't get a whole lot of shrinkage, we don't get a whole lot of stress, and we don't get cracking in the system. We see a slight expansion at the beginning. That's due to the heat of hydration. We see that that comes down to a baseline case that's slightly in compression. However, for the concrete that's in the plain concrete, we see that slightly after that initial temperature rise, we start to see shrinkage developing, and we start to see stresses developing inside of the steel frame. Those stresses are relieved at 3 different spots. Those 3 different spots refer to, 3 or 4 spots refer to cracking that's occurred inside of the concrete. So we see cracking very early on at the first day, day 3, day 5, and day 13, developing different cracks along the length of the rebar. So in the plain case, we see multiple cracking, and each time one of these cracks is opening, it's slightly changing the size of the other cracks inside of the system. But in addition to the width of the cracks, which is what's being plotted down here, what we can notice is that in addition to the crack forming, we're seeing debonding along the length of the rebar. And the amount of debonding depends a lot on the geometry and the stresses that are being built into the system. But we think that this plays a large role when we start describing the serviceability of these different concretes. So one of the things that I will mention here is that when we started to now pond the system with sodium chloride solution, and we ponded this over the cracks, we know the fluid is going to go into the crack very quickly, but we also know that this is going to spread in any debonded regions along the bar. We're using the sensors to detect where corrosion takes place, and one of the things that we noticed is not only do we see corrosion taking place at the center of the crack, at the location of the crack, but we see it spreading out for a long distance because of the debonding that's taking place along the reinforcing bar. So this is really important when we start to think about the role that internal curing plays. We have to not only consider the role that it has on the transport properties, but really the benefits in reducing the cracking in the system. That corrosion started within about a week, and the internally cured concretes were monitored for well over a year. No corrosion had started because you have the full concrete on the surface, no cracks. We're keeping the chlorides away from the reinforcing steel. So now I want to shift into the last portion of this talk, which will get into a few of the case studies and really talk about what people are seeing when they're placing these concretes in the field. Here you can see a plain concrete bridge that was being cast in around Bloomington, Indiana. There will be a second bridge that's cast next to it that's an internally cured deck. These are a conventional concrete mix that's shown here on this particular bridge. Here we can see the sister bridge, that's the internally cured bridge. These were implemented in about 2010. They were made using a conventional bridge deck, ready-mix concrete with conventional casting procedures and an internally cured concrete that was really what I would consider off-the-shelf technology. The only thing that was changed in these cases was to replace some of the fine aggregate with the fine lightweight aggregate, and this was a volume to replace the chemical shrinkage water that we've talked about before using the Benz equation. The only other difference that I would mention in this particular case is that instead of pumping the concrete, it was placed with a bucket. This was done on the first project due to potential pumping concerns. I will mention that there are no pumping concerns we've had on projects since then, and in fact we pump the concrete and don't have any additional problems with pumping the internally cured concrete because most of those, we have a high level of saturation, high degree of saturation in the pores, so we really are seeing that the internal curing is not really affecting the pumpability of the concrete at all, and we place it with pumps now on a consistent basis. Here we can see some of the results from those Bloomington projects. Here we see a slight increase in the strength of the Bloomington concrete. Compressive strength goes from about 5,000 psi up to about 6,000 psi. This is more than what was expected after 91 days. Again, as I had mentioned earlier, we typically expect to see a very similar overall compressive strength. When we look at information from bridge decks from New York, what we can see is a high-performance concrete shown in the center. On the right-hand side, we see a high-performance internally cured concrete, and what we'll notice is that the strengths are very, very similar at the same age in these cases. So very similar concretes being placed in a very similar way, very similar overall compressive strength. Here we can see some of the details on the mixture proportions. This happens to be the Bloomington project. Here we can see the water to cement ratio for a typical Class C bridge deck concrete in Indiana, and you can see the only difference is really replacing a portion of the fine aggregate with fine lightweight aggregate, and in replacing that we're also going to get water in that fine lightweight aggregate that's going to be our internal curing water. Everything else was exactly the same. It placed the same. There were no issues or any concerns related to placement. Now I've also shown here a plot that comes from a presentation by Bill Wolf where they're showing where the New York DOT has been using internally cured concretes, and here you can see that there have been several bridge decks being placed with internal curing in New York State. Now, what are some of the typical measurements that you'll see on site when you look at internally cured concrete and conventional concretes? Here we see a comparison of 3 of the bridge decks that we're monitoring. Plain concrete shown here on the left-hand side, internal cured concrete shown on the right-hand side. And we see for the high-performance internally cured concretes in Lisle and Tonawanda, New York, we see a very similar rapid chloride permeability between the plain and internally cured concrete. Again, in both of these cases, they're really high-performance internally cured concretes, so you're going to see very low RCPT numbers, and you're also going to notice that they're very similar from the plain to the internally cured concrete. In the Monroe County project, which was in Bloomington, Indiana, what you're going to notice is that the internally cured concrete has a slightly lower charge pass than the plain concrete, but this also is a higher water-to-cement ratio concrete that we're seeing that improvement in. In general, though, the takeaways, you're going to see very similar transport properties with the internally cured or the plain concrete when measured using rapid chloride permeability. Surface resistivity, again, the same type of result that we're going to see. Very similar response between the plain and the internally cured concrete. Slight reduction in the slightly more resistive internally cured concrete in Monroe County. Again, going with the fact that it would be more resistant to chloride ingress. Similar results shown here for the rapid chloride migration test known as NT-Build 492, which measures how far the chlorides penetrate into the surface. The internally cured concrete showed 15% less penetration at 90 days and 30% less penetration after 180 days, and that would result in a lower diffusion coefficient. This also doesn't even account for the fact that when we look at the internally cured concretes, we need to recognize that the open lightweight aggregate at the surface is going to allow chlorides in very rapidly. So when we're talking about that, what we're really talking about is when you cut the lightweight aggregate itself open, we will typically see that that surface lightweight aggregate will allow the penetration of chloride ions into those open pores at the surface, but the lower diffusion will take place over time and will really increase the overall diffusion decrease the diffusion coefficient, making it harder for the ions to get into the concrete. We've also performed similar tests using the Nernst-Planck type approach, and here we can see this using a stadium type of cell. Again, we see a lower diffusion coefficient typically in the internally cured concrete, despite having a slightly higher overall porosity because of the lightweight aggregates inside of the system. We've also done chloride ponding, where we essentially place the chlorides on top of the surface. We measure how far those chlorides go into the surface, and then we can backfit a empirical diffusion coefficient. And here what you will notice is that we typically see a slightly higher chloride concentration at the surface. This is mainly due to the chlorides entering the lightweight aggregate themselves, and we have more porosity at the surface, so very near the surface, the top 5 millimeters or so, we'll see a higher chloride concentration. However, as you get further away from the surface, getting down toward where the reinforcing bar is, what we typically see is a lower amount of chlorides, and at later ages we'll actually see that this becomes even less than a plain concrete in the overall system. Again, as I mentioned before, the reason for this being higher at the surface, the reason for some of the changes in maybe the NT build where you can see a higher concentration at the surface is because we have porous lightweight aggregates. There are large pores that are connected right to the surface. These will allow chloride ions in, but they're not going to be transported through the paste very quickly because of the more dense, dense paste system. But the main takeaway when we look at our internally cured concretes are we're going to have less cracks in the overall system. So we're going to be reducing the potential for cracking. This is a picture taken from one of those Bloomington projects. Here you can see the plain concrete where several cracks formed, 3 cracks that had formed and were monitored after 20 months, where the internally cured concrete showed no cracking after 20 months. Here again, the main takeaway is if the concrete cracks, it's going to allow the chloride ions in at a much faster rate than in an uncracked concrete, and that can play a role in the service life. Now I want to be very careful that even though this particular bridge deck showed no cracking when it was internally cured, we need to remember that cracks can occur for other reasons other than just shrinkage. So we need to be very careful to understand that while internal curing can help to dramatically reduce our shrinkage cracking, it may not prevent all the cracks that can form in the system. So what I really want to do now is I really want to try to wrap up and highlight the main topics that we've covered throughout Module 4 here. And what we've focused in on is the fact that internal curing is the use of lightweight aggregate. Typically it's going to be the fine lightweight aggregate that replaces a portion of the sand, and this will act as a reservoir to hide water inside of our concrete. That hidden water will come back to hydrate more of the cement, hydrate more of the cementitious materials, and this will help to reduce the porosity of our concrete. In addition, when we use lightweight aggregate sand particles, we'll notice that there will not be as large of an interfacial transition zone. So what we will see here is that we will typically depercolate the interfacial transition zones because we've taken sand out of the system and replaced it with a lightweight sand that typically doesn't have an interfacial transition zone. This will reduce transport properties because now we've got lower porosity because of increased hydration, and we have a reduction in the percolated transition zone. In general, we see very similar compressive strength. The coarse aggregate has remained the same. Most of the rest of the system has remained the same. The only real difference here is we've replaced a portion of the sand with lightweight aggregate sand. The idea here is that we're also hydrating more of the paste, so we typically see a slight increase in the strength of the paste, resulting in a very similar compressive strength of our concrete. Internal curing is going to reduce fluid transport. This will be reducing absorption. This will be reducing diffusion. This will lead to reductions in the ions entering the system and causing corrosion. So this will delay the time to corrosion and will increase the overall service life of our concrete. The final takeaway is that the internal curing is being implemented, and when it's being implemented on bridge decks, very positive things are being noticed with a reduction in the overall cracks that are forming in those systems, and very similar, if not improved, transport and strength properties are occurring in those cases. So in general, we're getting a similar strength because we're increasing hydration. We're getting a slightly lower elastic modulus, and you may say, well, that doesn't sound like it's good, but a lower modulus is beneficial because it essentially makes the concrete easier to stretch, if we think about it in that way. So when concrete is restrained, we're getting a lower buildup of stresses in the system, which is going to make it less likely to crack. Lower modulus also means we're going to have lower microcracking taking place in the system. Freeze-thaw resistance, we generally see a similar behavior to plain concretes, provided we have proper air entrainment. And remember, the self-desiccation is going to pull water out of the lightweight aggregate. So after a relatively short period of time in a low water to cement ratio concrete, we're going to have pulled the water out of the lightweight aggregate to cure our concrete, and we're not going to have a problem with the water remaining in the lightweight aggregate. So in general, internally cured concrete is going to behave very similar to plain concrete, provided both cases have proper air entrainment. We saw that there were some benefits in ASR and sulfate attack, mainly because of dilution effects with ASR, but also both are going to provide a little bit of additional space for expansive products to form, which will reduce some of the stresses in the system. The main takeaway, though, is internal curing is going to help to reduce shrinkage cracks, and shrinkage cracks are really the Achilles heel of higher performance concretes because these cracks can lead to corrosion. So by taking these out of the system, we can help to improve the service life of our concrete by reducing the cracks, which are going to provide a short circuit for chloride ions and other things to get to the reinforcing steel, so we can improve durability that way. Transport properties are typically going to be similar or improved with internal curing. We're typically going to see a slightly lower diffusivity, slightly lower rapid chloride permeability, or lower electrical properties. We talked about a few of the artifacts that can occur, such as the cut surfaces leading to higher chloride concentrations, for example, at the surface, or conductive aggregates if we start to use more than just the internal curing volumes that can actually change some of our resistivity values. We need to be very careful if we start replacing large volumes of the aggregate because the conductivity can actually change some of our electrical measurements. But in general, for internally cured concretes, our current recommendation is to test them the same way as conventional concretes and to ignore the effects of the conductive aggregate, and we're going to be conservative in doing that. Finally, internal curing has the ability to reduce chloride transport. This is going to have implications on the time to corrosion, but it also has the ability to reduce cracks that form, which is also going to have a major impact on the time to corrosion, and it's going to increase the service life of our concrete. With that, I would like to thank you for tuning in to the fourth module of internal curing, and if you have any questions, please feel free to email those questions.